let's have a look at some different polynomial theorems. The first one being our remainder theorem. So, if you want to divide a polynomial by a linear factor, turns out that the remainder is always polynomial A. So whatever you get when you substitute A. Let's prove it. So there's our division algorithm, as they call it. So polynomial divisor times quotient plus remainder. Now, if we're saying the divisor is x minus A, so we'll rewrite it with the divisor being x minus A. So let's find polynomial A. Well, polynomial A then, in that factor of x minus A, that becomes 0. So all I'm left with is remainder A. So polynomial A is remainder A. Well, that's close to what we want. We want it to be remainder x, not remainder A. But we know the degree of the remainder is always less than the degree of the divisor. So if the divisor is linear, then the remainder has to be a constant number. So the fact that I've got remainder A doesn't matter. It's going to be constant no matter what I substitute in. So remainder A would be the same as remainder x, would be the same as remainder. So yes, remainder x will be whatever we get when we substitute A into the polynomial. So there's our proof. So let's use it. So find the remainder when it's divided by x minus 2. You don't have to do the division. I can just substrate in. Polynomial 2, when we calculate it, turns out to be negative 19. So okay, there's our remainder. Fair enough. Let's now make the remainder theorem more useful. And we'll turn it into the factor theorem, because at the end of the day, that's what we want to do. We want to factorise polynomials, and we want to find them without, well, too much work. Well, if it's a factor, I know there's no remainder. So I can use the remainder theorem, but now we just call it the factor theorem. If that turns out to be 0 when I substitute it in, that means there's no remainder. There's our factor theorem. It must be a factor. So that's all the factor theorem is. It really is the remainder theorem, but forcing the remainder to be 0. Show that x minus 2 is a factor, and hence factorise it. So I substitute in. Oh, what do you know? We get 0. Fantastic. We now know x minus 2 is a factor. But remember, the factor theorem is saving us from doing polynomial division. But I now have to factorise it. So I do polynomial division to work out what the other factor is. Sort of defeats the whole point of using the factor theorem. But let's do it. X and x cubed is x squared. Bring it down. 0 minus 2, positive 2. Okay. X to the 2x squared. That'll give me 2x. Expand out. Minus 15x plus 30. X in the minus 15x minus 15. Oh, what do you know? The remainder is 0. What a surprise. So that's what I mean. It sort of defeats the purpose of using the factor theorem, because when I did the polynomial division, I came down to a remainder of 0 anyway. Why bother with the factor theorem? Now, of course, the reality is I wouldn't do a polynomial division. But let's just finish off our factorisation here. The other factor, x squared plus 2x minus 15, multiplies together, give minus 15, adds together, give 2. We get 5 and negative 3. There's our complete factorisation. Reality is this. I mean, this is where factor theorem comes in useful. Okay, we know x minus 2 is a factor. I've got to factorise it. A little bit of simple logic will factorise it a lot quicker. Because if we were to think about it, whatever answer I get, if I was to expand it out, I should get the original question. And we know that when we expand out a polynomial, the leading term times the leading term must give the leading term. So x times something must give x cubed. Okay? So leading term times leading term must give me the leading term. X times, I wonder what, will give me x cubed. Well, it's got to be x squared. I can do the same thing with the constant. The constant times the constant must give me the constant. So negative 2 times something must give me 30. Negative 2 times what? Gosh. Oh, negative 15. That just leaves me with a middle term to work out. How many x's are in that middle term? So what I now do is I say, well, if I was to expand out now, how many x's would I have? Well, at the moment, if I expand it out, there's only one expansion that's going to give me something x, and that's the minus 15 times x. I've got minus 15x, but I want minus 19x. So therefore, minus 2 times this middle term must give me the rest of them. So how many do I need? I need minus 19. Well, how do I get from what I have to what I need? Well, I need another minus 4x. Whoa, minus 4x. Negative 2 times what? Oh, rack my brain. Minus 2 times that missing term. So that's got to be 2x. There's the middle term. I could have done exactly the same with x squared. I mean, I chose to say how many x's do I have. I could have done x squared and came up with the same answer. That's what I call just doing it by logic. Other people call it doing it by inspection. But personally, I think that's a heck of a lot quicker than doing a whole division. Let's do another. Now this time, I've been given no hints at all. The other one had told me, oh look, prove x minus 2 is a factor. No hints. So I just got to randomly pick numbers to substitute in and come up with 0. Now, of course, I don't really do it randomly. There's some logic behind the choice. For instance, I'm not going to look at this and go, I wonder if 7 will work. I mean, that would be a silly number to choose because there are certain rules. Constant factors must be factors of the constant. So I know it has to go into 36. That gives me possibilities. I purposely chose 36 because it has so many factors here. So it could be 1, it could be 2, it could be 3, it could be 4, it could be 6, it could be 9, it could be 12, it could be 18, it could be 36. But of course, who's to say it's a positive number? So they could be negative as well. But then in this case, because it's not monic, I could have a fractional solution rather than a whole number. Now, all your fractional solutions will be in the form of factors of the constant divided by factors of the leading coefficients. And I picked 4, it's got a few factors as well. So, not only could I have 1, 2, 3, 4, 6, 9, 12, 18, 36, I could have all of those numbers divided by 4, because 4 goes into 4. Mind you, some of those I've got already. I'll cross those out. 4 over 4 is 1 and 12 over 4 is 3. So I don't know, I've repeated those. But of course there are other factors of 4. 2 goes in as well. So it could be any of those numbers over 2 as well. But again, I've doubled up some there. So let's get rid of our double ups that we don't need. Righto. Oh, well, the only other factor is 1, which that's obviously the whole numbers. Oh, but of course they could be negative as well. So I've got lots of possibilities. As I purposely picked these numbers, so we had lots. In most cases, you end up with a very few to check. 1 or more of these will be a solution. So logically, which one would you do first? Yeah, of course, because 1's an easy number to substitute in. So that's why I chose 4. Okay? And, oh look, it turned out to be 0. Wasn't that lucky? So, I now know 4, or x minus 4, is a factor. So I got rather lucky with my original choice there. In case you're wondering, no, it probably wasn't my original choice, but just you're right, I probably would have gone with 1 first of all, because it is so easy to substitute in. So, okay, I know x minus 4 is a factor. Let's work out the other factor using a bit of logic. Now, the leading term times the leading term must give the leading term. So x times 4x squared. Now the constant. Minus 4 times something is 36. Minus 9. The middle term. Something x. What do you want to check? The x's or the x squared? Your choice. X squared? Okay. If I was to expand this out at this stage, how many x squared have I got? How many do I need? Bingo. That seems to imply it's done. If you're feeling uncomfortable, check the x's as well. At this stage, how many x's do I have? Minus 9x. How many do I need? Bang, I'm done. There's the factorisation. There is no middle term. I'll just complete the right-hand side. 2x plus 3, 2x minus 3. Heck of a lot quicker than doing a polynomial division. Let's pick an HSC question out to look at. 2004 HSC. They've set up the polynomial for us. X plus 1, x minus 3, qx, and so on. A and b are real numbers. That's handy. Divided by x plus 1, we get negative 11 as the remainder. And when we divide it by x minus 3, we get 1 as the remainder. What is b? Well, they've told me polynomial negative 1 will be negative 11. Remember, that's our remainder theorem. Sub that in, bingo, I got it straight away. Fantastic. See, that was the logical piece of information to use, because the negative 1 got rid of the a, it got rid of the first bit as well. So I've got b. Thank you very much for that, Mark. So what is the remainder when we're divided by x plus 1, x minus 3? Well, that's a quadratic. So the remainder could be linear. Might be a constant, could be linear. So this ax plus 1 plus b is the remainder, if you like. Okay. Polynomial 3 is equal to 1. So that tells me 4a plus b is equal to 1. So I now know a is equal to 3. So there's my polynomial. X plus 1, x minus 3, qx plus 3x minus 8. So 3x minus 8 must be the remainder, because the rest of it is factorised with x plus 1, x minus 3. 3x minus 8. Here's another one. Let's just suppose we've got this cubic, and we know that when we divide by x plus 2, we get a remainder of 3. That's basically what that's saying. Find a. We know polynomial negative 2 is 3. That's what the right-hand side's telling me. When I divide by x plus 2, I get a remainder of 3. Now, they might not have said it in those words, but that's what that expression is telling me. So if I use that on the left-hand side, subbing in, we get our value of a. So eventually, there it is. So a is 19. So they might not use words. They might just set it up like that. Polynomial divided by x plus 1x minus 4. Quotient qx, remainder rx. Y. Oh, you love these ones, don't you? Where you've got to actually explain rather than do the work. Y is the most general form given by that. And I guess what they're looking for there is something like this. That you know that, hang on, my divisor's degree 2. It's quadratic. Therefore, the highest degree of the remainder must be less than that. So it must be 1. Now, it doesn't necessarily mean that it will be a linear function. It might be a constant. Okay? But it would be the most general form, a linear function. Now they give us a bit more information. Given the polynomial 4 is negative 5, show that remainder 4 is negative 5. Okay. Well, there's our algorithm. X plus 1, x minus 4, qx plus the remainder x. If I sub in 4, look what happens. The first bit disappears, and I get that the remainder 4 must be negative 5, because the remainder 4 is equal to polynomial 4, which they told me was negative 5. Further, when it's divided by x plus 1, the remainder is positive 5. Find that actual function, rx, ax plus b. Okay, well I now know remainder 4 is negative 5. I know that. So 4a plus b is negative 5. Okay. They've now told me that when I divide by x plus 1, I get positive 5. Minus a plus b is 5. See, the actual calculations there are not hard. It's coming up with the equations. I mean, that's where the work is. Solve them simultaneously. A is negative 2. I know A is negative 2. Have we worked out B? Not yet. Let's sub back in. So B must be 3. We know the remainder is AX plus B. So it's minus 2x plus 3. There it is. Alrighty, so 4D, just a little reminder here. If the factor is 2x minus 1, then when you're using the factor theorem, it's a half that you put in. Basically, just ask yourself, what would make that equal to 0? That's what you substitute in. Okay.